All right, we're going to try to do some math. So we have derivatives from section 3.1 to 3.3a. So this is stopping before the product rule and all that stuff. We're not ready for that yet. This might be a doozy of a video, so please bear with me. We are going to try to hit the definition of a derivative, and then talk about some differentiability implying continuity, and then we will talk about some rules, but not all the rules. So let's give it a shot. So here we have the definition of our derivative, and there's two ways of writing it. Oh, wait, sorry, not definition of the derivative. This is the difference quotient. Difference quotient is actually super nifty because we're looking at effectively a change in y over a change in x. So that's looking at a slope. And we can write it in a different way where we can make this change, this x minus a, into some variable h. So this is the change that we made, the change in our x values. So we're making this small change in the x values, and then we're making that small change in the x values in the denominator, and we end up with something that is the exact same as that difference quotient that we looked at up above. So difference quotient, super important, because I wonder what happens if you take the limit as that little difference goes to 0 of your difference quotient of f of a plus h minus f of a all over h. I wonder what will happen. You're looking at a slope still, right? Because this is a slope. Change in y over change in x is a slope. But that slope is also a limit. And a limit is a number. Interesting. All right. So now we got the definition of our derivative. So the derivative of a function f at x, which is our input, is given by f prime of x equals the limit as delta x goes to 0 of, and this looks like the difference quotient, f of x plus delta x minus f of x all divided by delta x. Another way we can write that is using our other difference quotient formula, f prime at c. So now we're evaluating at a particular number c. C is a number. And we're looking at the limit as x approaches c of f of x minus f of c, which is a delta y, divided by x minus c, which is a delta x. Lovely. And provided this limit exists. So this limit has to exist, otherwise we don't have a derivative. These are all going to be functions of x. So f of x and f prime of x. We don't change our independent variable. There's different notations. This one is one that we normally use. This one is also one that we normally use. This one is 2. This one is when we feel fancy, and this is if you're an engineer. So we're not really using this because in this class we're treating you like you're mathematicians. But here is looking at our dy dx notation. This one is, I think this one is the Leibniz one, and then this one's like the Newton one. I actually don't know who came up with this. Sounds like good topics for your journal. All right. So how do we find the derivative of f of x when f of x equals x cubed plus 2x? Well, let's use our limit as, let's call it h. Approaches 0 of f of x plus h minus f of x all over h. And plug in what we know. Limit as x approaches 0 of x plus h cubed plus 2x plus h minus, and then I'm going to put parentheses because that's responsible. I don't know why there's lines here. Sorry about that. But we have x cubed plus 2x, and this is all over h. That equals, and look, I'm not dropping my limit notation because a limit is a number, not an expression. So then let's expand this out and avoid the freshman's dream. The freshman's dream is just distributing this exponent there. That is not something that we do. When I was a TA in college, that was something that we laughed about. All the people who were grading things like professors and stuff like that. So don't do the freshman stream. You need to use the distributive property and multiply out. So what is that? We get, this is like a Pascal's triangle thing. We get x cubed plus 3x squared h plus 3x h squared plus h cubed plus, and I'm going to distribute this to, boom, boom, we got 2 x's plus 2 h's minus x cubed minus 2x all over h. So now I'm going to change colors because that's fun, and then we have this x cubed, pew, pew, that cancels out, and then we have a 2x, pew, pew, those cancel out, and what's left? I'm going to write this, we're going to scroll down a little bit. Unless we can't. Okay, so I'm going to scroll down and we have limit. Because we have not yet evaluated our limit. We have 3x squared plus 3x h plus h squared plus 2. And I'm factoring out my GCF of h. And that's all over h, so pew pew. Those go away. This equals, and now I can evaluate my limit, right? I can plug in h, because before if I plugged in h I would have gotten divided by 0. That's not a thing, that is undefined or indeterminate, and so we can't handle that. So we just need to work with some algebra so we can get some stuff that we like. Alright, so now we have 3x squared, there's no h's there, so that doesn't go away. We have 3x squared. We have 3xh, but the h is going to 0, so that goes away. This h squared, 0 squared is still 0, and then plus 2. Boom. There is my limit. 3x squared plus 2. Does that make sense? If we look at our original function, we're looking at a function of x, and yes, we have a function of x, and yeah, that looks good to me. Alright, moving on. Find f prime of x, so the derivative, for f of x equals square root of x. Then find the slope of the graph at the points 1, 1 and 4, 2. Discuss the behavior of f of x at 0, 0. Okay, so first of all, let's just sketch what square root of x looks like. Boom, like that. Okay, so at 0, 0, let's discuss the behavior at 0, 0 first. So can we find, like, f prime? Can we look at the slope of our tangent line? Because that's what our derivative is. It's looking at a slope of not a secant line, but a tangent line. Tangent meaning instead of it hitting our function at 2 points, we are just grazing our function in at 1 point. So is there a tangent line? Can we figure out what our slope of our tangent line is here? Well, I think that actually might be undefined because you don't have anything to work with on this side. So your limit is only a one-sided limit, and we don't like that with our with having a limit that exists. So we're gonna say that our f prime at 0 does not exist. Cool. But I worked backwards. Focus, concentrate, Ms. Contreras. Okay, so we have f prime for f of x equals square root of x, so I need my limit. As x approaches, well, yeah, as h approaches 0 of square root of x minus h minus root x all over h. And this looks like something that we can attack with a conjugate. Root x minus h plus root x all over root x minus h plus x, root x, and this is 1, right? So we can handle that. That's good. Okay, cool. So I'm not dropping my limit notation because I'm being responsible. Limit as h approaches 0 of, and I'm multiplying very intentionally by the conjugate, which is difference of squares thing, right? So if you have like a squared minus b squared, that equals a minus b times a plus b. So I manufactured a plus b right there. So then we can just get our a squared minus b squared terms. So we have x minus h, and then when I multiply everything else, it cancels except for a minus x times root x times root x, which is x all over h. X minus x, pew, pew. Those cancel. Oh, I need a denominator though. Being irresponsible. I'm just so excited to be recording. Alright, so now we have limit as x approaches 0 of negative h over h times root x minus h plus root x. And now I have pew pew h's that cancel. And so now I'm left with equals limit as h approaches 0 of negative 1 over root x minus h plus root x. Now I can evaluate because I don't have an indeterminate form, and I get negative 1 over square root of x plus 0, that's root x, plus root x, that's 2 root x's. And that is my derivative. That's the slope of my tangent line, and that will give me a number at 1, 1. So I just plug in 1, right? I plug in this left one. So if I plug in 1, let me change colors. So if I plug in 1, f prime, I didn't change colors. Okay, so if I, yeah, is it worth it? It's not changing. Okay, so if I have f prime at 1, I'm evaluating this. I have negative 1 over 2 root 1. What's that? Negative 1/2. If I try to evaluate f prime at 4, 2, I'm plugging in my x value. So f prime at 4 is negative 1 over 2 root 4. And what is that? That's negative 1/4, because 2 times root 4 is 2 times 2. 2 times 2 is 4, and my numerator is still negative x. Negative 1, excuse me. So that's pretty cool. All right. Moving on. So how do we find the derivative with respect to t of the function y equals 2 over t? Well, limit as h approaches 0 of 2 over t plus h minus 2 over t all over h. And this looks really gross. We should probably try to, well, we can multiply by a super denominator if you want. Or we can just multiply by the reciprocal. Actually, I'm going to leave that up to you and try to solve that. And then, so I'll put up a question and then you can answer that. And then I will proceed. So, let's see. How do I want to do this? Well, I think I want to do as 2 over t plus h minus 2 over t all over h. I think I want to multiply, instead of writing this as all over h, I think I want to multiply all of it by the reciprocal of h, because division is not actually a different operation. It's just multiplication by the reciprocal. And then, what does that leave me with? Limit as h approaches 0 of 2 over h times t plus h minus 2 over t times h, th. Alright, and then I still don't have a common denominator, so I need to fix that. Limit as h approaches 0, and look, I'm still not dropping my limit notation because all of these are numbers. So I have 2, and then th minus 2, oh, I didn't need to multiply by the h there. Okay, and then I have 2 times t plus h, And then my common denominator is t plus h. And now, what do I get? Limit as h approaches 0 of 2t minus 2t minus 2h all over t plus h. Lovely. Pew, pew, those cancel. Pew, pew, those cancel. What are we left with? Negative 2 over t times t, which is t squared. Boom, derivative. And we're doing this with respect to t, so it makes sense that our derivative is a function of t. Cool, cool. Moving right along. Differentiability implies continuity. So your task is to make a video of yourself explaining why this is true. So think about how you're going to explain why differentiability implies continuity. Remember that the existence of a derivative means that this limit exists, or that, like similarly, limit as x approaches c, which might be more useful here, of f of x minus f of c all over x minus c, differentiability means that this limit exists. So try to think about how you're going to justify that, and you need to make a video of yourself explaining that to someone you live with, someone who is older than you, who you live with. They don't have to like be in the frame, but they do need to be apparently there somehow. Have them like wave and then jump out of frame or say hi or something. Whoa. All right, constant rule. Okay, so this is a function that's a constant. Look at that. Wow, it's wild. What's the slope of that line? What's the slope of all the lines tangent to this curve? Well, it's 0. What if you put it like all the way up there at like positive a million, all the zeros in the world? I don't know how many zeros that is. It's a lot. I think it's a billion. Positive a billion. Well, if it's still a flat line, then the slope of our tangent lines is still going to be 0. Even if it's like pi, derivative of pi is going to be 0. All right, don't forget that. The power rule. Okay, so this is lovely. So this is our binomial expansion. So this is what Pascal's triangle is nice for. So if you don't remember what Pascal's triangle is, just go ahead and Google that. It's quite lovely. And then this is our binomial expansion. And these are all like really nice rules for things. So then we have like, this is a generalized version of these 4 examples. So if you're looking at, say, f prime of x for f of x equals x to the n power, then this binomial is going to be actually like part of your derivative, right? Because if you have limit as delta x approaches 0 of f of x plus delta x, that means that you have x plus delta x to the n power minus x to the n power, all divided by delta x. Yes? So then, and I'm going to be really lazy here. I'm sorry about the laziness. So if we're looking at the limit of all of this, which is x plus delta x to the n power, and then I'm just going to sneak this in, this limit as delta x approaches 0, it's really small, minus x to the n power all over delta x, and then pew pew, those two cancel, and then x, delta x is a term, is a factor in all of these, right? We have one delta x there, we have delta x squared there, and presumably, you know, for the rest of them, there's going to be more and more powers of delta x. So then one of these goes away, this one goes away, and this one becomes n minus 1 because this cancels with that guy. So then what's left over? Well, we just have n times x to the n minus 1 from right there. And then all these other terms, pew, they go to 0 because our delta x, which is a factor in all of these other terms, is going to be 0. So this is like plus, just like a really fancy 0. But since we're mathematicians, we also get lazy and we don't write 0. So look, lovely. N times x to the n minus 1. We just reduce the power and multiply by what that power was, and we find what our derivative is, as long as we're working with x to some n power, or we're looking at a power, not an exponential function. Pretty cool. So voila, it is the power rule. If we have a rational number n as our exponent, it also works for irrational numbers. So you can go ahead and like trust that, but for this definition, we don't include the irrationals. And so the function f of x equals x to the n is differentiable, and we know that its derivative is n times x to the n minus 1. In order for our function to be differentiable at x equals 0, because remember with x to the 1/2 power we were looking at, or sorry, we can write it like this, square root of x. When we were talking about that didn't have a derivative at 0. And so in order for in order for our function f to be differentiable at x equals 0, we also need an interval containing 0, so that we can our function needs to be defined on an interval containing 0. So the problem with the square root function is that we don't have an interval that contains 0. That's part of our domain for the function. All right. So try out those derivatives and see how you do. Pause. All right. So f prime is 3x squared. Just take the power and reduce it by 1. G prime 1/3 x, and then we have a 1/3 minus 1, which is negative 2/3. And here we have y prime is, well, this is x to the negative 2. So then I take my power out front, x to the negative 3, because of negative 2 minus 1 is negative 3. All right. So how do we find the equation of a line tangent to the graph of f of x equals x squared when x equals negative 2? When is that going to happen? Well, we need to figure this out using our derivative, right? Because that gives us our slope of our tangent line. But then we also need to just find that point. So we can do that as well. So f of negative 2 is negative 2 squared, and that's 4. So we have a point negative 2, 4. That's going to be part of our line. And then we need to find the slope of our line. So let's just take our derivative, f prime of x equals 2x, and plug in what value? The x value that we're looking at, because we need the slope at negative 2. 2 times negative 2, positive times a negative is negative, and we got 4. So do we square that answer and we're good to go? No, absolutely not. We need an equation of a tangent line. So what is the equation of that tangent line? I think it's y minus 4 equals negative 4 times x plus 2. If you want to do more than that, that's nice, but I'm not going to. All right. If you have a differentiable function and you have a real number, c, then c times our differentiable function is also differentiable, and you just take that scalar out. This is called the constant multiple rule or the scalar multiple rule. Scalars are not vectors. Vectors are magnitudes with direction, and we're not ready for that yet. But if you don't believe me, then we can just justify it real quick. So if we have the limit as h approaches 0 of f of x plus h minus f of x, all over h, and then we multiply by some constant like that. Well, look, it's a GCF. We can just factor that out. We got c times this limit as h approaches 0, because limit is a number, right, of f of x plus h minus f of x all over h. And this is our f prime of x. So we got c times f prime. Boom. Done. Because a limit is a number. And a derivative is a number. A derivative is the slope of our tangent line. Alright, so I'm going to pause the video and then let you work on these. Alright, so now we have dy dx equals, well, this is 2 times x to the negative 1, so I have a scalar multiple, so I got negative 2 x to the negative 2. Cool. F prime of t, this is 4/5 times 2t. Let's write that a little better, 8/5 t. What about c? When I write this with the dy dx notation, just because I feel like it. This is 2 times x to the 1/2 power. So when I take this 1/2 and multiply by 2, I just get 1, and I'm lazy, so I'm not going to write that. And then I have x to the 1/2 minus 1, which is negative 1/2. There you go. Okay. Ooh, look at this. This one looks interesting. We have 1/2 times x to the negative 2/3 power. Lovely. Dy dx, what is that going to be? Well, it's 1/2 times negative 2/3, and I'm going to throw parentheses there so I don't accidentally subtract. And then I have x to the, and then negative 2/3 minus 1 is negative 5/3. So that means I get negative, and then pew pew, get 1/3 x to the negative 5/3. And y, I'm going to write this as y prime because I'm feeling lazy now. Oh, that's just a line. What's the slope of that? What's the slope of the tangent line to that line? It's always going to be 3/2, right? A negative 3/2, excuse me. All right, moving right along. So if we're looking at derivatives which are numbers, then if we add numbers together, we're still good to go, right? We can do addition nicely, so that's good. We can also do subtraction, which is actually just secretly addition, right? Because this is f of x plus c g of x with c equals negative 1. So addition and subtraction are the same. I don't know why we separate them, but we shouldn't. So addition and subtraction with our derivatives, it works like we think it will. Think about for a minute if multiplication or division with functions works with derivatives in the same way. Because in essence what we're doing is the limit as h approaches 0 of f of x plus h minus f of x all over h minus f of x, g of x, excuse me, plus h minus g of x all over h. We're just like rearranging the order of these. That's what we're doing. So does that work with the product or the quotient? Probably not, because I'm making you think about it. All right. Look, these are all sums of things. We can figure that out. Here, try that on your own. All right, so if we have f prime of x, that's what? Power rule, so 3x and then 3 minus 1 is 2, minus 4, and then that x, this just goes away, right? So it's just 4, because x to the 1 minus 1 is 0, and then that 5, well, the derivative of any constant is just 0. What about b? Try b. So b, the derivative of b is going to be, so we have negative 4 over 2, which is negative 2, x to the 3rd power, plus 3 times 3 is 9, x to the second power, minus 2 times x to the 0, which is 2, and boom, there you go. So last thing, I think. Oh, no, it's not the last thing. Oh, well. So this is sine and cosine and e to the x. So our derivatives of these, if you think about them like intuitively, I guess they mostly make sense. Maybe e to the x doesn't totally make sense. But if you think about like this, if the derivative is the slope of the tangent line, then here, where I have zeros of my tangent line slope, that's going to correspond to where I have zeros of my derivative. So there's like a lovely connection going on there. But do think about how you would prove at least one of these, because that will also be an assignment for you. Huzzah! It's pretty cool. I would probably attack these with some of our limits, like some of the special limits that we knew. That would also maybe help quite a bit. All right, so how are we going to take these derivatives? Let's try to do y prime. Yeah, we haven't done that one in a while. So we got 2 times sine of x, derivative of sine is cosine. So we got 2 times cosine of x. What about b? We have 1/2 sine of x, which is the same as sine over 2. Okay, well that's y prime, and then it's just a scalar multiple on sine. Derivative of sine is cosine. What about here? Dy dx. Well, this is going to be derivative of x is just 1, because it's got a leading coefficient of 1. And plus, if it's a slope of a line that has slope 1, then its slope is always 1. And then plus cosine. So cosine's derivative is negative sine of x. Cool. So average velocity is looking at the change in the distance divided by the change in the time. If you are looking at velocity at a particular time, like an instantaneous rate of change, then you're going to be looking at a derivative. So average velocity is just a slope, but the instantaneous rate of change, or the velocity, is the derivative of position. Here we're saying that position is s of t, and for parabolic motion kinds of things, we tend to use this formula. You might have seen it in physics, you might not have, but here you go. 1/2 g, which is the acceleration due to gravity, t squared, plus v naught t plus s naught. So this is the initial position, this is the initial velocity, and this is how gravity is affecting the thing, and that will tell you the position. Why does this 1/2 come about? Well, that's an interesting question. I think you can probably justify that to yourself using derivatives. All right, last thing, there's a calculator skill that you want to learn. There's Math 8 on your calculator. It's nice. Also, if you haven't downloaded the calculator Google Chrome extension, there is a TI-84 Google Chrome extension if you so desire. Okay, I'm going to leave this for you, actually. When does the diver hit the water? That's probably going to be when does s equal 0? At what time does s equal 0? And what is the diver's velocity at impact? That's probably what's v prime at that t that you found. T impact. Try to figure that out. Alright, so when does the diver hit the water? Well, if we're looking at, this is our position function, 0 equals negative 16t squared plus 16t plus 32. I don't want to deal with all of those things, so I'm just going to factor out a negative 16. T squared minus t minus 2, because I factored out a negative 16. And what's that? Negative 16 times t minus 2, t plus 2, plus 1, plus 1, okay. And then where are my zeros for that? Well, that's t equals 2 and t equals -1. Does negative time make sense here? Absolutely not, because we're starting at time equals 0. So after 2 seconds, that diver is going to be hitting the ground, hitting the water. Oh my goodness, hit the water. Okay, so the diver hits the water at time t equals 2. What's the diver's velocity at impact? Well, we need to find our velocity, which is, that's not a v prime, it's just a v. V at t impact. So v of 2, what is that going to be? Well, we need v of t in general, which is our derivative of our position. So what is that? -16 times 2 is -32t plus 16. So then v of 2 equals -32 2 times 2 plus 16. And oh yeah, the derivative of 32, that goes to 0, right? Because that's a constant. So what do we get? We get -64 plus 16, and that is more effort than I feel like. It's like -48. What are units? Feet per second. T equals 2 seconds. Boom. You could do this with Math 8. Just plug it into your calculator, the function, and you can take a derivative. It's really nice. All right, I think that's it. I'm just gonna stop it now, if I can figure that out.